So good morning everybody. Uh, Today we start the course Introduction to Smartphone Computing. So I will be taking 3 classes uh, on this, and the 3 classes would mainly concentrate on localization. Okay. So talking even before going to localization, let us talk a little bit of let me give you some small introduction of smartphone computing. Uh, like this, we know that almost all of us now have smartphones. Okay, almost all of us surely have mobile phones, and I guess almost 90% of us will be having smartphones. Okay, and so talking about what is mobile computing, if you see that today's access to information and computing service is necessary everywhere, and it has become a need of humankind that you can access information and computing service. So it becomes ubiquitous, and not only from our home base but also while we are traveling and when we reach a different location, even when we are in between on holiday, we want some sort of access to information, and this is actually possible through mobile computing. So what is mobile computing? If we just try to say in some words, that techniques that allow mobile users to use portable computing devices to run standalone applications and or to access remote ones via wireless network. So with mobile computing, another important thing is, say, mobile computing and what is related is wireless network. Okay. So one important part of mobile computing is wireless network, and when we talk about we have told that we will talk about localization. Okay, so that is clear to all of you, I guess, that we will talk about localization. And what is localization? Localization is location awareness. Okay, location awareness of the device. And when we talk about that, one important component would be actually wireless network. Okay. So coming back to the slides, so if you see that mobile computing is a simple by a simple definition, it's a computer while on the move. So you can think that, and many of the our modern smartphones are actually much more powerful than, say, a computer 10 years back. Okay. So how did everything begin? Just to say that 1980s to 1990s, you see, so again, mobile phone has to do with wireless communication. And what happened in 1980s and 1990s? Consistent innovations in wireless communication. You began to see consistent innovations in wireless communications. Okay. Some of them are like, you see that the mobility, so you see the H850 HSPA, then the LTE coming, the LTE EVDO. So all sorts of different standards and different sorts of wireless technology comes, and which actually, what was that doing? All this technology initially established connectivity. And what type of connectivity? Initially established voice connectivity. Okay. So initial standards, if you see 2G, even 3G, there are, so so the GSM, 2G, etc. I'm sorry, uh, etc. were mainly consisting, mainly concentrate on developing good voice connection. Okay, mainly developing good voice connection. But as we move through 3G and then LTE, what is happening? Actually, we are concentrating more on data connection. So voice is also becoming a part of data. So previously there was voice and data. Okay, at the end, at the beginning there was only voice, then there is voice and data, and next it is data where voice is a small part. Okay, so this way how technology, the wireless technology developed and the standards developed, so that all this so that what we can do, we can actually support a lot of data communication rather than voice communication, and lot of data communication. And how does it help, we will see. Okay, so as soon as, so there, this is one interesting thing about technology and business. Okay, so this is one interesting things about technology and business, that okay, you have actually developed a very good, you have actually developed a very good system, that's fine. Okay, you have actually developed a very good system and a very good technology, but that technology so quickly become commoditized. Okay, so what happens, that all companies then can make it. Okay, so a particular company really having a lot of revenue is not possible. Okay, so long term revenue stream becomes unclear. Okay, so especially for big companies with high overhead cost. So as soon as a technology is established, this is a dilemma of technology, a good technology coming, but companies cannot actually have profit out of it for long term. So what companies have to do then? The companies have to actually constantly innovate. Okay, so companies has to constantly innovate. What does innovate means? Bring in new services, bring in new services to actually, so you have to bring in new services. So you have to continuously innovate, bring in new services to really benefit out of the base technology. So a base technology, no matter how good it is or how good you make it, it won't survive long. Means it will survive long, but it won't survive the profit motive long. And you know, our society is still driven by profit, and if some product is profitable, then only it actually gets popular. So that realization makes the emergence of apps. So which we know, so one of the most popular apps which all of us may have used is Angry Bird. Okay. So what is this sort of apps? This sort of apps are actually built upon the basic innovation of mobile technology. These sorts of apps are built upon the basic innovations of mobile technology. So you see, this is a picture of Steve Jobs, who actually first realized that apps and services are key. So that's why Apple is not a company which makes just a iPhone, but it actually built up a dynamic ecosystem. It actually built up a dynamic ecosystem where there are Apple market, iPhone market, and this iPhone market, you see a lot of apps which people can actually use, and which people can actually use and get a lot of benefit. Okay, so the point is very simple. The point is that base technology is coming from wireless. Okay, and there are other things, but ultimately this has to be, because base technology would just support voice. Okay, base technology is just supporting voice. Fine. Now this voice gives very less revenue. Okay, very less revenue. Okay, and so this base technology has to be enhanced with apps, and that's why you see now most of the communication within mobile phones or between mobile phones is on data rather than I'm sorry, rather than apps. Okay, rather than voice. Okay. So if you just sample in and see your mobile usage pattern, you will see that calling through mobile phone actually now has become a very insignificant part. Okay. You see, check your mails, you play, okay, you can see Facebook, okay, you download Google Maps. When you are going to some place, you do Google Maps. So all these sorts of things you do with your mobile phone, and which is nothing to do with the original message or original mission of transferring voice. Okay. So, then uh, what you see, now let me talk about the base technology once more. So what is the base technology? What we are saying? We are telling that the base technology is wireless. Okay, base technology is wireless. But if you go to the mobile phone, unknowingly we have also put on several other technologies. Okay, like you have a good CPU. Okay, good CPU. Okay, and also the other thing is there are a lot of sensors. Okay, there is a lot of sensors which we can use. Okay, so some of the usage of sensors, if you think that if you rotate your mobile phone this way, your screen also rotates. So what happens if rotate mobile phone, then what happens? Screen also rotates. How does it happen? How does it happen? This happens because there are sensors like gyroscope, okay, which understands, what does it understand? Which understands the, motion of the mobile phone, motion of the mobile phone. Okay. So as soon as you have these sensors, which are some of the sensors are like accelerometer, gyroscope, okay, a compass, okay, and many other things, the voice sensor. So everything is a sensor, the voice sensor, the camera. So all these are actually the light sensor. Okay, you can have light sensor. So all these sensors actually helps us a lot in developing innovative apps. Okay, so these things which have been put just so many times we hear that we have many things in our mobile phone which we actually never use. So we have this criticism against mobile phone that who uses camera. Okay, so this was a criticism maybe. So I remember at least 5-6 years ago, people would say, give me a good robust mobile phone rather than give me some with some fancy camera which I will never use. So people were conservative and they were thinking in that way. But slowly what is happening, many of these accelerometers, many of these sensors are being used either by the user directly, like camera. We know that so see this culture changes so hugely that previously we couldn't even think about taking selfie, and now selfie has actually become a rage, and this has become suddenly a norm as if we were taking selfie for the last 100 years. Okay. So anyway, so what is happening? What is the app store doing? So again coming to Steve Jobs story, what he has made, an app store, and in that app store you can actually get all these apps and be all these apps and at least be reasonably hmm, reasonably hmm, reasonably sure, be sure that you are not getting any malware. Okay, no malware. So no malware is a strong statement, but I am telling that this app store or Google Bazaar, okay, Android Bazaar, what are they doing? They are actually giving a place for developers to showcase their apps and also having some regulation so that you are reasonably sure that you are not getting any malware. Okay, so you can see this picture of how many work and you see the growth. Okay, so there are 10 billion. Yeah, I think I am showing 2012 data and you see that a number of uh, downloads cannot be matched. Okay, but okay, so what has happened? See, most these apps are actually very low hanging fruits, and again by the law of economics, what would happen? These apps can make a little bit of money for some time, but slowly they will actually become less profitable because they become a common thing and people would not be interested in buying that as a premium service. Okay, so after sometimes initially it's a premium service, okay, but slowly it becomes a common service. Okay, so what is the need is that all these low hanging fruits are most probably done by now. Okay, so mobile phone, smartphone, why are we talking about smartphone technology? So we are in Kharagpur, we are actually offering a full term course on smartphone technology, and I guess all of you have seen there is a website, people are doing it. So why so much importance given? Because all these low hanging fruits would be gone very fast. Okay, and it is almost going. Okay, so how many times you can build an angry bird? Okay, so YouTube, etc., Google, all these things are done. So what would happen is you would actually need a lot more innovation. So this picture says that getting harder to make money off apps, startups heavily will leverage business innovation, technological underpins would have to arrive for, there has to be technological underpins, technological innovations. Just simple putting things together would not work, and so you need a new technology building blocks, ideas which are crucial. So we need new technology building blocks. Okay, so yeah, so this is again maybe something um, too too gigantic, but actually you need fertile imagination, deep research and execution. All these three things would be actually needed. So let us see what are the some of the apps which we can have slowly. So see, I like this app. For example, say you have phone sensors on, whenever you are driving, your phone senses owner driving and blocks incoming call. So this is a simple app, but it's very difficult because see what are the technological challenges. If you think of the technological challenges, that how will the phone understand that the person is not driving or sitting beside the driver? So it's not so easy to understand that whether your owner is actually driving or sitting beside the driver. So it needs a lot of precision. We have to do a lot of precision, a precise calculation or precise predictions, so that this type of false things doesn't happen. So it's not a simple thing. It needs a lot of technological. I'm just telling you some of the applications. I am telling you some of the applications, you can think of many again. Okay. The other thing is, so this is an interesting thing. So this is something which we call as augmented reality. Okay. So what is augmented reality? So this is what we call augmented reality. So what is augmented reality? So augmented reality is, say when I see, I am seeing this person. I am seeing this person, Carlos Tevez, but also and Robinho and Bellamy, so other players. I am seeing these players. Now, what is happening is not only, so when I see through my plain eyes, when I see through plain eyes, I see the person. But when I will see through the device, then his name, his history, everything would be augmented. So it is reality, but it has been augmented. Okay. Now what is happening? Say, I don't know if anybody of you see this television serial Person of Interest. Okay. So if some of you see this television serial in Star World, okay. So you will see that there is some sort of augmented reality, that when you are coming, when I am seeing you, not only I am seeing you, okay, but also getting a lot of information about you. Okay. So this is again the idea of Google Glass that way, okay, Google Glass that way, okay. So there are criticisms about this augmented reality, that whether it will infringe in privacy, okay. People will have no privacy, etc., etc. But still, augmented reality is an interesting application which will come. So what is needed to do this? Okay, or let me take this. This is a picture which I like very well. So I will come to this picture. Say you are driving and you come to a place and you see a house at the top of the hill. Okay, you are driving and you see a house at the top of the hill, and now you place your mobile phone and ask that, how I wonder how much it costs to live there. Okay, you put your mobile phones up there and ask that, how I wonder how much it costs to live there. Okay, and then it sees and tells you that it cost dollar for 7.8 billion 8 million. Okay, so as a professor, it's not possible, only you can see it. Okay, so what is happening essentially, an interesting thing is happening is, see, this is becoming a Google in real space. See, now when I type in Google, say smartphone computing, so I don't get any location wise thing, but now I am telling that, see this location and tell me the history of it. Okay, so it is actually happening that we are actually developing a Google in real space. And remember that what we have to do for this sort of applications, that you have to understand location very well. Okay, you have to understand location very well. Okay, so let me go back to other applications. So the other application is like smart home. So we say smart home. So there is a lot of discussion about smart home, smart city. So smart home would be a very feasible applications, that reading focused bright light here, watching TV diffuse light from kitchen, okay, cooking defocused moderate light. So as soon as the activities goes on, the mobile phone or the sensors begin to understand what is exactly happening there, okay, and accordingly take actions. Okay, so sensors. So see, important thing is, again, this is very interesting, that initially what was the technology, means I am just thinking from a technological underpin also. What was the technology which we were actually too much concentrating on wireless, and still we are concentrating. You know that there is a lot of talk about spectra, sharing, etc., etc. Then now Airtel has come with 4G, okay, and also it has run into some sort of trouble, but there is a search, or there is a consistent effort to make wireless and accordingly wireless more seamless. So also for all these apps, wireless would actually become less and less important, and sensors, the inbuilt sensors inside those apps would become more and more important. Okay, would become more and more important. So this is how things would go. This is how technology will actually develop over time. So other thing is again another interesting point about sensors is, see, we all have this Google chat or Google in Facebook also, and Google, what we see that you get green or black or yellow or red or nothing when accordingly the person is present, person is in don't disturb mode, person is idle, but we actually don't get this information. Say we want to get that information whether the person is sitting, whether the person is sitting, or whether the person is running. Okay, can we get this information? So in our Google Maps or in our Google chat, okay, Google chat or Hangout, whatever you say, we don't get this information. Okay, in Google Hangout or Google chat, we will not get this information. But if we have sensors, okay, sensors, if we have Google Hangout or Google Chat, but if we have sensors, now see what is happening. Sensors will have activity recognized, okay, and also it can have location recognized and say that this person is in open space or this person is in a restaurant, this person is in house, okay. So there are two things, one is activity and location, and that can come as small smileys or small pictures in your Google Hangout and Google. So this is a simple application. Really, if you talk how to monetize it, we don't know, but this is a very innovative application, and think that this couldn't have been done previously even if we had thought, and now this can be done very seamlessly even without users explicitly telling it. Okay, so this makes me actually the I am slowly coming into the localization topic. I guess you are understanding the entire perspective. So what is happening, just to sum up, what we see is that there is the research. If you think in terms of research threat, there are two types of research threat. Okay, two research threat. What are the two research threat? One is bottom up, from bottom to up, another is top to down, and one is bottom to up, means you are actually trying to make the wireless networking much better. Okay, and here one important thing is energy is an important thing. Okay, so you want to make the battery life much better. So what you want to know or do that, you want so there is a lot of work what tries to actually access wireless or access connectivity, both Wi-Fi, GSM or 3G, whatever you say, much energy efficiently, and doesn't want to waste a lot of energy. There is a lot of work that how you actually access this wireless connection so that energy doesn't get drained out in your mobile phone. Okay, and there is a top down approach. You can see this top down approach where we are actually talking about much more application oriented things like localization, which we will cover more detailedly, like activity and gesture recognition, or like psychological computing. Okay, so So we are actually working on a project where as soon as you type, the mobile phone will understand, okay, so will understand that whether you are happy or sad or angry, okay, it will begin to understand your mood through your typing speed, your typing pattern, how many mistakes you are making. So those sensors are used actually to understand. Fine. I guess you are uh, uh, getting a lot of idea. Anybody has any question? Anybody has any question? And I can take it before I start on the localization part a bit more deeply. Because what you understand that so if you, I'll just put forward, let me, I hope some of you are actually accessing my my web page on smartphone computing. Is somebody of you accessing my smartphone computing web page? So if you go here, courses, smartphone computing, okay. So where I teach energy, localization, cloud, etc., etc. So it is going on. So please follow this, and you will see that there are lot of work. So what we are trying to do is just cover localization in this. So let me come to introduction to localization. So what is localization? So what is localization? Localization is simple thing that understanding where you are. Localization is understanding where you are. So this seems to be very see, this seems to be very simple if you think that this seems to be very simple. But say I am telling you that my in many cases, if I say my localization, my where I am at 11° north and 32° east. Okay, if I tell you that where am I? I am at 11° north and 32° east, which is very what to say, which is actually very, because we will not understand. But if I tell that I am in NKN room, okay, I am in NKN room, that is much better, although this may be not precise as the previous one. Okay, this is not, this is very precise. Okay, this is very precise, while what is this? This is more semantic. Okay, so this is much more semantic, while that is more. Okay, so what happened is that, see, I tried to give you a lot of idea about how things work, okay, and how industry is moving. So you see that sudden what happened, people immediately begin to understand that if you want to build up a lot of apps, localization or location is very important, because location would actually add value. Location would actually add value. Okay, so and what is happening? Localization technology was caught unprepared. Okay, was caught completely unprepared, and so a lot of need is there, but the technology was not so much developed. Okay, so this is a small thing. What we see that according to forecasters, actually 2.8 billion. See this 2.84 billion. So dollar 2.84 billion. Okay, it is almost close to India's economy. Okay, not exactly India's economy, but it is very good, very big. That would actually depend on localization, because most of the ads would actually become, most of the ads would actually become local ads, because people would try to make targeted ads more and more and local ads. So localization of the mobile phones would be much more important. Okay. So we know that how so with emergence of Hotstar etc., what is happening, people are also seeing their TV serial not through TVs but through mobile phones. So what is happening, one traditional technique is GPS, which we will actually study. So we will study GPS in this class. One traditional technique is GPS, which we will study in this class. But what are the apps which is needed, and we will see that whether GPS would be good enough. So what are the criticism against GPS? First, what are the good things about GPS? If we think about the good things about GPS, the first good thing is GPS is very accurate. What are the bad things about GPS? GPS is very power hungry. Okay. The other thing is, most of this localization, if you think carefully, most of this localization would actually be, see, reminders when passing a library, targeted ads in Starbucks, Walmart, information about paintings in museum, access file from this room. So like one of the applications which many of us think that we will have students, it may be also, since many of you are students, you may also think in that line that since say you give an assignment to the students and they are connected through Wi-Fi, but only people inside the class should be able to actually submit the assignment. Others who are outside the class should not be able to submit the assignment. Very simple thing, but this would actually need some sort of localization, because if you have a mobile tower, this mobile tower would actually can be accessed by people even outside the class. Okay, so this is a small problem, but very interesting problem, very difficult problem. Okay. So what is happening, if you think, most of these apps, many of these apps are actually working on indoor localizations. Okay, many of these apps are actually working on indoor localizations, which is not possible in GPS. Okay, GPS would work well when it is outside, but inside GPS would not work. Okay, fine. So then just to think of the enabling technology, what are the enabling technology we need? We need outdoor continuous. Okay, we need indoor semantic. Okay, indoor semantic is also very interesting. Then I told you that I am in NKN room, or I am in a restaurant. This sort of localization is needed, where exactly which restaurant etc. may not be immediately important, but I need a restaurant concept. Okay. Second is, say, high precision indoor. Okay, what is high precision indoor? Can you give, I will tell you some of the applications of an high precision indoor. So high precision indoor is like, high precision indoor is simple. What happens in high precision indoor? In high precision indoor, you will see that, see, these are two restaurants, R1 and R2. Okay, R1 and R2, and you are sitting here. Okay, and now say we have various location based services like Yelp, Foursquare. Okay, some of you may be knowing this location based services, Yelp, Foursquare, etc. Now what would happen that if you sit here, maybe Yelp or Foursquare will actually give you some price, if you are in R1. Okay, will give you some price if you are in R1. So how can that be achieved, that precision be achieved, that even when this guy is not just beside R1, this localization should be able to understand that he is not in R1 but just beside R1 and in R2. So what we need is high precision input. So many of the application would actually need very high precision. So take another example. Take another example, like I am in a museum. So I am in a museum. Okay, I am in a museum, and what is happening? I am in front of a museum. I am in front of a photo, and when I take out my mobile phone, I take my mobile phone, okay, and I see whatever it is written. It gives a history about whatever is written in of the photograph or of the painting. Okay, many times it happens you see the painting, and if you don't have a mic or a guide, that's very irritating. You don't understand. You may appreciate some of the picture, some of the beauty of the painting, but the beauty also comes, or the appreciation of beauty also comes from how good you know about history. So this is very important, that appreciation also comes when you know about its history. Okay. So you may be knowing this, that top musicians has performed in New York subway without being noticed. Okay, there are lot of stories where top musicians without revealing their identity has performed in New York suburbs without being noticed. Okay, so this is another thing. So you need outdoor continuous, indoor semantic, high precision indoor, and also precise object localization. Where is that object? So I take a object and try to localize them. Okay. Okay. So let me proceed. I guess all of you can see my slides. Okay. If there is any problem with the slide, please let me know. Okay. So now let me come into the global positioning system, GPS. Let me talk about GPS in more details. Okay. Let me talk about GPS in more details. Okay. So what is GPS? So GPS is like, there are worldwide radio navigation system forms a constellation of 24 satellites. So if you see, there are actually 24 satellites from which you can, these are man-made stars, from which you can actually get reference points to calculate positions. So these were actually originally made for US Air Force or US Army, but I guess after some years they actually decommissioned it and made it available for public. Okay. So with advanced form of GPS, you can make measurement better than a centimeter. Okay. So good thing is GPS receivers. So initially, if you see GPS receivers, you will see that GPS receivers are big receivers. Okay, so they are big receivers. But now what has happened? GPS receivers have been miniaturized to just a few integrated circuits, and so are becoming very economical. So GPS receivers are economical. So this is important. GPS receivers are economical. So now you cannot go and buy a mobile phone which will not have a GPS. So you can go and tell that I want a mobile phone, cut the price by maybe 50 rupees, 100 rupees and give me a mobile phone without GPS. So that is actually not possible. So what is happening? GPS has become very economical and it has become a part of mobile phone, and GPS can be find anywhere. So in advanced country we find it cars, boats, planes, construction equipment, everywhere you find GPS. Also now in our country, in cars people are using GPS. GPS is becoming very popular in our country also. Okay. So what are the four primary functions of GPS? I will talk about one is position and coordinate. Okay. So let us write one is position and coordinate. Okay. Position and coordinate. Okay, and then with that the distance and directions between two waypoints. So you can have the distance and direction between two waypoints. Okay, distance and directions between two waypoints. This is possible, and then making about that you can have travel progress report, and also since GPS clocks are very accurate, you can also have accurate time measurement. Okay. So you can have accurate. So you have position coordinate, you have directions. So if you run on a GPS phones, you will see GPS assisted cars. Then you see that the car is instructed by the GPS. So it gives the direction and dial and travel progress report, and also a very accurate time measurement. Okay. So this is also very important. Fine. Very good. So GPS works in three logical steps. The basis of GPS is triangulation from satellites. So we'll come to talk about triangulations. Okay. So to triangulate, a GPS receiver measures distance using travel time of radio. So I am here, the satellite is here, and I see the time, and this is the time. Okay, and there is another satellite, I see the time. Okay, and from that time what I can get the distance. Okay, I can get the distance. So I get distance from 3-4 satellites, and accordingly I can understand where I am. Let us see. Okay. So there is so along with the distance you need exactly where the satellite. So what you need to know? You need to know where it is. Okay, you need to know where it is. So these are satellites. Okay. These are satellites. Fine. I hope all of you are understanding. Okay. Finally, but then there are so high orbits and careful monitorings are secret, but finally you must correct any delays the signal experiences as it travels through air. So it may not be that so the traveling time will vary according to temperature, according to climatic conditions. So remember that it will actually vary according to climatic conditions. So all those small adjustment has to be made to get very accurate results. Okay. So this is about GPS. So now let us move into a more technical part and try to understand. Even before that, let me tell that what does the GPS sense the satellite. Okay, the global positioning satellite GPS, the global positioning satellite What they sends the ID to identify which satellite is transforming. So they send the ID, and then they send data about the status, current date and time, and also tells the receiver where each GPS. So this is called ephemeris data, ephemeris. Okay. So see that this is called ephemeris, where you get what? You get status, current date and time, and after that what you get? Almanac data, where it says where each satellite should be at any time throughout the day. So it gives some sort of prediction also. Okay, it's some sort of forward information. It gives some sort of forward information. Okay. So you have satellite ID, then you have status, and then you have forward information. Okay. So one is called ephemeris data, another is called alphanumeric data. So this is again the same picture which I was telling. Signal leaves the satellite at time t, then signal is picked by the receiver at time t plus 1. So what is the distance traveled between satellite and receiver? 3 times the speed of light. Okay. So what is the distance traveled between the satellite and the receiver? 3 times the speed of light. Okay. So you have 3 times the speed of light. So you know the distance. So this way what happens is you begin to know the distance from the first satellite, then you can again know the distance from the second satellite. Okay, you can know the distance from the third satellite, and you can know the distance from fourth satellite, and so on. So let us see that your distance means what? What does this distance means? Means there is a sphere. This is a sphere. Okay. So this is a sphere. Now you know from the second one. So then this is also a sphere. So what does intersection of two spheres? Intersection of two spheres gives you. What does intersection of two spheres gives you? So intersection of two spheres will actually give you a circle. Okay, the intersection of two spheres would actually give you a circle. Okay, so what does interaction of three spheres give? Now if I take three spheres, the intersection of three spheres. So 1, 2, the third. So intersection of two spheres, 2 gives circle, and if I do a circle and sphere intersection, then what would it give? It would actually give 2 points. So if I take 3 satellites, then it is actually giving 2 points. Okay. So 2 points, and so what are you getting ultimately? You are getting 2 coordinates, 2 x y z, x1 y1 z1, x2 y2 z2. So one thing is very simple, that if you see x1 y1 z1 and x2 y2 z2, one would be impossible. You will see z is the height. You may see this height is say 5,000 feet or 50,000 feet. Let us put it in a. So it may be that means even in a even in a plane, if you are not in a real fighter plane, you must 50,000. So, one is impossible, another is possible. So, what is happening? This is why it is called triangulation. With three GPS stations, you can understand what is your location. Okay. So let me again repeat it. I guess repeating it would be good. So what is happening? You are a person standing here and there are GPS. Okay. There are a person standing here and you know the distance from here. You know the distance and you know the distance. Okay. So what does this distance means? Means you know the distance and you know its coordinate. So you know its coordinate, but you don't know your coordinate. Okay. You know the coordinate of the GPS station. Okay. Of the GPS station. Okay. So satellite, but you don't know your coordinates. That means what? Your coordinate may be, where would be your coordinate be? In a sphere where both the GPS station and you are are diagonally opposite. Okay. So if you think in a sphere where both of you are diagonally opposite. Okay. So now I take the second one. Okay. When if I take a second one, then also it would be the same thing. So now what is happening? We can now think that you are basically somewhere here. Okay. Now I take a third one, and third one also gives us sphere, and now I can say either you are here or you are here. Okay. So then now I see that your position has been pinned down by 3 of this into 2 points. Okay. So if you take a fourth one, what would happen? Fourth one, then it should actually pin down into the exactly the point. Okay. Now actually pin down again to the same point. Okay. So it is something like a if I write simultaneous equations. So forget about 3 points. So if I have 3 equations, say if I have x plus y is equal to 5, y plus x, y plus 2y plus x is equal to 7. So then we will get a value of x and y. Okay. Now if I have the third equation, 3x plus 5y is equal to 15. Okay. So what can happen? What can happen? Tell me if I write the third equation. So this is the question I am asking you simple now, that I have two unknowns. So what is happening? Again, even before going, let me make it very clear. What is happening? I want to localize. What I know two things. I know the location of the satellite and I know the distance between me and the location of the satellite. So what I know the location of the satellite. Let us admire locations of the satellite and distance between myself and the satellite. Okay, I know these two things. Anybody has any question? Okay, I know these two things. Very good. Now what I am trying to do? I am actually trying to. So I know satellites. I know three satellites. If I know 3 satellites, what is happening? I would get 2 points. If I know 4 satellites, I will get basically 1 point. Now what happens if I know 5 satellites? Then also technically I should get 1 point. Okay. How? So now I am just thinking in a bit of mathematical terms. Okay. So making life easy. So if I have a sphere, what would happen? A sphere would actually have a distance equation in terms of x, y, z. Okay. It would be a distance equation would be in terms of x, y, z. Like if you can write, I can write it and show you x minus x1 whole square plus y minus y1 whole square plus z minus z1 whole square. Okay, where x1, y1, z1 is what? The coordinate of the satellite. Okay. So you have x1, y1, z1 which is the coordinate of the satellite. Is that okay? Okay. So essentially what is happening, you see, you begin to get sets of equation. So now think carefully. See, I am making life easier. I am telling it is fxy and I am trying to find the equation where there is just x and y. Forget about this problem. Okay. And I have 2x plus 3y is equal to 5 and x plus y is equal to 2. So what would be the solution? X will be is equal to 1 and y is equal to 1. Okay, the solution of this equation is 1. Now I have a third equation, say, which is says 3x plus 2y is equal to 6. Is it possible? So see, the third equation has to be consistent. So the third equation has to be consistent. So because if I put 1 here and 1 here, this will be equal to 5, but you are getting 6. So the third equation is not consistent. But now think of practical situations. So what I have shown in this as a situation that 1 you get sphere, 2 you get circle, 3 you get 2 points, 4 you get 1 point, okay, 5 1 point and always 1 point, but there will be errors. So this distance calculation would have all errors. So if I take the first 4, it will put a point somewhere here, say somewhere here. If I take the next 4, say take this next 4, it will put the point somewhere. So it will not be exact 1 point. It would not be exact 1 point. There will be actually deviation. So in pure mathematical terms, what we think that consistent equations, these equations won't be consistent. So just think carefully, the equations won't be consistent. So equations won't be consistent. So then what do we do consistent? So what do we do when equations are not consistent? But equations are roughly same. So again I have written 2x plus 3y is equal to 5, 3x x plus y is equal to 2, and I have written 3x plus 2y is equal to 5.2. So it is almost close to this, but there are some errors. So there are some noises and there are some errors. Okay. So then I have to do some sort of minimization of this error and see that minimization of this error and find this point where the error would be minimum with respect to all the equations. Minimization of this error and error would be minimum for all these equations. I will come to detail. Okay. So error would be minimum for all these equations. Fine. So again, very clearly, let us think carefully what we have told. See, we are getting some distances. Forget about satellite, but we are getting distances. So we know 5 positions and 5 positions, my distance from these 5 positions. I don't know my position, but I know 5 different positions. I know, and I know my distance from these 5 positions. So essentially, what does it mean? That I am actually, if I think these 5s are like circles, if I build spheres around these 5 positions, if I build spheres around this 5, so I think this picture was somewhat misleading. It is that I build spheres around this 5 position, not that this is circumference. I build spheres around these 5 positions with this the distance. Okay, then the intersection of these spheres would actually give, because with I think that satellite is in the center and I am in the sphere. So intersection of the spheres would actually give my position, but this intersection would not be very consistent as we see in consistent equations, because there will be error, there are technical errors. So in essentially we have to develop a system where we minimize this error. Okay. So I guess even if you have not understood fully that entire thing, but just try to understand the basics, that we have equations which equations are not consistent, and so we have to, but they are not too inconsistent. It is not that 3x plus 2y I have given as 75. I have given it as 5.2, a little bit inconsistent, but I have not given it as 75. Okay. So now I am trying to devise a system where this inconsistency will be taken care. But even before that, there are other issues. Okay. Number one issue is, how do I understand the location of the so there are two important issues. Now let us dig deeper and think of two important issues. One is, how do I understand what is the location of the GPS satellite, because what is happening when I am receiving the signal, the satellite also has moved a bit. Okay. So I have to understand the location of the GPS satellite and exact time of traversal. How do I understand? Because what is happening, that I have a clock, this phone has a clock and GPS has a clock. Okay. These clocks are not synchronized. Okay. These clocks are not synchronized. So say your how I am getting, so I am getting your first time. So I am getting t minus t. Okay, this t is calculated in a GPS and this t is calculated in my mobile phone. Okay, so there are two different clocks. Okay, so there are two different clocks. So how to actually adjust two different clocks, because my clock may be telling that time is over, please leave the class, and but your clock is telling, sir, the time is still half an hour left, so go on taking the class. So there are no synchrony. So remember, there are no synchrony, and synchrony is not possible. Synchrony is not, that would take huge amount of. So your clock has a bias and mobile's clock, GPS clock has a bias and mobile's clock also has a bias. Okay. So try to understand. So this is one interesting thing which we have to actually take care. So think, so see this, that satellite distance. So what is happening? Basically I am reading T and say I am reading T, the satellite is reading TS, but essentially I have a bias delta tau and satellite also has a tau s. So essentially my thing is T, my real time is T, okay, and the receiver's real time is T and the satellite's real time is TS. So essentially what is the distance? If you think c is what? Speed of light. C is speed of light into T minus T. Okay. Essentially E S T minus Ts. Fine. So if I write it more systematically, then what is Ps at T is equal to, because T is T plus tau and Ts plus tau s into C, which is T minus Ts C plus C tau minus C tau s. So these are bias. Okay. So think carefully before even I progress, that you have. So we are telling that there is real time. Real time is capital T, but I am reading T and there is a clock bias which I know is tau. Okay. And also the so there is an atomic clock somewhere where from where we are calculating the biases. Okay. So there is also another time tau s, another time real time Ts is the real time of the satellite, and but satellite has given Ts and tau s is basically its bias. So essentially my real distance is this, and so that can be explained like this. So if I do a little more of this, yes, you will see that you are actually, I wrote it even before that excess tau s. So what is excess xt? So if this is basically, what is this? The x axis of the satellite, the x position of the satellite at Ts. Okay, this is essentially the x position of the satellite at Ts. Okay, so but there is another interesting problem, that how to estimate this Ts. How to estimate this Ts, because you see, yeah, so this is problematic because when we receive it, it may not be exactly the position it should be. Okay, so see, we note one complication, that the satellite position must be calculated at transmission time Ts. This is important because the satellite range can change as much as 60 meters from the time the signal was transmitted, okay, to the time the signal was received, approximately 0.07 seconds later. Okay. So if the receiver were used instead, the error computed in the range could be tens of meters. Starting with the receive time T, so now what we do, we try to adjust. say we write the so first we assume that Ts, so we do a iteration to actually calculate Ts. So we say that Ts is equal to T initially. Okay. So Ts is equal to T, which is T minus tau. Okay. Very good. But it cannot be T because there has been time taken to actually transmit. So there has been time taken to actually transmit. So then it is actually T minus rho T minus Ts0 by C. Okay. Ts1 is that. Okay. So what is Ts1? It is basically, I am telling that no, it cannot be so less. So it will be, so say these two are same time. So these two are same time. First these two are same. Okay. First these two are same. Now taking this time, I am calculating the distance. Okay. So what is happening? Again, if I go to the previous question, what is happening is I have to calculate, I have to get XTS. Okay. So XTS is not known. So now I am thinking that fine, forget I don't know, I take XTS as T. So XTS and T is same. And then fine, then I do a iteration. So initially I took XTS as T. Then but STS cannot be T. Think carefully, because STS TS should be at least less than the distance travelled. This is the distance, this is the time travelled. So if I go back to this picture, at least it should be, because it started from here, it came to here. So at least it should be this time travelled. Okay. So I am just adjusting the time. See, I am just giving a minus. So it should be this. Okay. So if this is this, then again take it Ts2, make T minus rho s T1. Okay. I take T minus Ts1. Okay. I do an iteration and go on unless and until what happens, unless and until I see that there is no change in the next iteration. There is no change in the next iteration. What does that mean? So I calculated Tsi is equal to what? T minus rho s T minus Tsi minus 1, okay, by C, and Tsi plus 1, what is this, is equal to T minus rho s T Ts I by C. And if Tsi equal to Tsi plus 1, then stop. That means the system has converged and I get the exact time. I get the exact time when the satellite have started. And as soon as I get the exact time, I can understand the exact location. Okay. So now again coming back, what are the two problems we were tackling? Distance between myself and satellite. So this is what we see, although we talk in one line, this is not a simple thing, that exact time of traversal is not a thing, because you have to know the location, etc., etc. Okay, location very carefully. Fine. So now you know the location and you calculate the time, and finally what are you arriving at? Finally, what are you arriving at? You are arriving at a set of equations like P1 is equal to x1 minus x whole square. So what is happening is, this is with respect to satellite 1. So this is with respect to satellite 1. Okay, and this is with respect to satellite 2. Okay, P3 is with respect to satellite. So for each satellite, so now with all this calculations and with all this fine tuning, what we are getting, for each satellite we are actually getting the exact distance equation. So where did we start? Again, if we come back and think, what is happening is, if we have distance equation, exact distance equations, then how many equations would be good enough to solve? The good enough would be 3 equations or 4 equations, and the fifth would be basically coming to the same point as the fourth. If you remember that I have one equation, it is sphere. Second equation, I get circle. Third equation, 2 points. Fourth equation, 1 point. Fifth equation, 1 point. So now we have actually, but this equation finding was not easy. It had to do some sort of manipulations. Now we have actually some equations, but unlike the original equation, see here, two things are still there, that C tau and C tau minus. This is not gone. Okay, this we have to take into consideration, bias. So here you have the biases and the 3 equations all together. Okay, so there are actually, if you think that clock bias is also unknown. So let us think that the clock bias of the satellite is known. Clock bias of the satellite is known because it's a precise device. It can tell you the bias of the satellite, but the clock bias of your smartphone bias is not known, because knowing exact bias would be very difficult. So now what were we left with? We are left with series of equations. Okay, maybe 5, 10. How many at most we can have? Perhaps 24. Okay, so we have series of equations and 4 unknowns. What are the 4 unknowns? X, Y, Z and tau. And equation Pi, again I am writing, although it is written there, it is x minus x square, xi minus x square plus yi minus y square plus zi minus z square plus c tau y. Okay, so these are the series of equations we have. Okay, so in order to solve this sort of equations, actually what we do a thing which we can call as Taylor's theorem or Taylor series expansion. Okay, Taylor series expansion. Fine, we do what we call as Taylor series expansion. Okay, so what is Taylor series expansion? Let us go to the next slide. Okay, so what is happening is, there is observed and there is model. Okay, so there is model and there is noise. Okay, so what is happening? We solve the point positioning problem by first linearizing the pseudo range observation equations and then using familiar methods of least square analysis. So we are doing a least square analysis, as I told you that we will have a least square analysis to solve it. For completeness, we summarize the linearization procedure and the development of least square methods specifically for GPS point positioning problem. First, we assume we can write the actual observation to be the sum of modeled plus observation. So let us assume that model plus an error term, which is noise. So what is model? So there is some error still, but model is P, X, Y, Z, T. So this is a model. So this is basically a model. Okay, this is basically a model P, X, Y, Z, tau. Okay, so this is basically a model. Now we apply Taylor's theorem, where we expand about the model computed using provisional parameters x0, y0, z0, tau 0. So we have provisional. So let us say that we have provisional parameters x0, tau 0. So let us not worry too much about these parameters. Okay, these are provisional parameters. We will talk about in detail. So if you have this provisional parameters, basically you can have a Taylor series expansion by some partial differentiation, and you have x, y, z, tau. Okay, then the equation x0, y0, z0, tau 0, and then plus x minus x0 dp dx, and in this way for all this, and let us ignore the higher order terms, then you get this equation. So ignore the higher order terms. Okay, ignore the higher order terms. Okay, so you get P computed and you get the delta x dp dy del y, and in this way dp dy d tau del tau. Okay, very good. So once you get this, now what is del p? Is p observed, whatever is observed and whatever is computed. Okay, and that is simply the differentiation. Okay, so del p is simply the differentiation. So now you can write del p is equal to, in a more matrix form which I have written there. Let me write it once more for your clarity. Dou x p dou y dp dz dp d tau, and del x del y del z del tau, and the v term still stays. Okay. So now you have dp. So what is this dp? Now if you think, dp is basically this delta p is can be again expanded into delta p1, delta p2, and accordingly delta p. And here you can write p1x, and you can accordingly form the matrix. Okay, you can accordingly form the matrix, and you have del x del y del tau, and you have the noise for each equations v1, v2, and vn. Okay, so just try to get a gauge, it is fine. So you can basically write ax plus b. So what are you trying to get? What are you trying to get? You are actually trying to get the x's, because this will give you the coordinate, because you are not interested in all this equation etc. Only thing interests you is the coordinate. So just to understand what is a, see this a, this is a, okay, this is a, this is a. So how to find this a? If you see this equation, if you see this equation and if I differentiate over say x, then what I will get 1 by root this same thing. So this is rho. If I get 1 by root this, 1 by root this, 1 by root this is rho, and then x is 2. So you will get, okay, let me write it and then you will be clear. So if I have P1 is say root x1 minus x0, okay, this way you have and plus something, okay, and this is say rho, okay. So if I do it, it will be 1 by half x1 minus x0, okay. The same thing, this thing will come down, and if I do this, this is square, so if I do this, this will be 2 x1 minus x0. What I am doing? dp1 differentiating over just x. The all others become constant, so all other goes, this 2 goes. So what happens here? x1 minus x0 by rho. Okay, the same the rho, if this is rho, this is also becoming rho. Okay, so then see what is this A equation? A equation is basically x0 minus x1 by rho, y0 minus y1 by rho, z0 by z1 by rho, and here there was c tau. So if I have differentiated, it is just becoming c. Okay, if I differentiate, it becomes c. So this is the equation. This is the matrix. So now what we have? We have V is equal to B minus AX bar. Okay, and so now what is the least square solution? The least square solution can be found by varying the value of x until the following function is minimized. So unless the noise is minimized, so what I am trying to find? The x, the estimate of x. See, think carefully, the estimate of x where the noise is minimized, where the noise is minimized. I want to find the estimate of x where the noise is minimized. Very simple. This is one point agenda. I want to find out the estimate of x where the noise is minimized. And how do we minimize? We have a least square method. And what is least square method? We know that this is Vi square summation, and that is how VTV, V tau B, and that can be written as is V minus AX tau and B minus AX. Okay. So just to think about what is AX. AX is a n cross n matrix divided into this. So this would give this into this. So this would give just a 1 cross n matrix. Okay. So this would give a 1 cross n matrix. Okay. And similarly, so this is also this is giving a 1 cross n matrix. So this is a 1 cross n, and the tau is a n cross 1. So this would actually give a single number. Okay. So this into this would actually give a single number. Agreed? Okay. I guess all of you agree. So now just to solve, so if I get Zx, how to minimize Zx? So we know that if I differentiate it, and if that differentiation is 0, then that is minimization. So the I2 Zx is equal to 0. And what is del Zx means? Now you have B minus Ax tau. See, I am just doing the steps which are there. Okay, I am doing the steps one by one which are there. Okay. So B minus Ax bar is equal to 0. Okay, and then you do the differentiation so by parts. Okay, so you keep this, you do the differentiation by parts. So you differentiate this part b minus ax tau into b minus ax bar plus b minus ax tau and delta b minus ax. Okay, so you do differentiation of this part and then do differentiation of this part, and if you do it, what you are getting is basically, if you are doing this differentiation, this is very simple, it is minus a delta x tau, okay, transports, and b minus ax, and this is what, this is b minus ax t, and this is minus a delta x. So again this is a, so we can understand that this is a 1 cross n and this is a n cross 1. So if I just shift it, it won't be, so if I just make this ax a delta x tau and this as b minus ax, it won't actually affect. So I just make this and make this, it won't affect. And then but for ours it becomes, the next line you see, it becomes very simple, 2a delta x tau b minus x is equal to 0. And then what happens if I just take ax t a t b minus a t a x bar. You see it, if you do it, it comes like that. Okay. So if this is 0, this should be 0, and if this is 0, if this is 0, then what happens, a t a x bar is equal to a t. So what was happening, again see that if this into this is 0 and none are negative, okay, so so we know that a into b is 0. What does that mean? That either a or b is 0, and this part cannot be 0 because delta xt is basically the numbers which cannot be 0. If that is 0, then all the, what is delta xt? It is the coordinates, that coordinates cannot be 0. We means, what is delta xt? You are calculating the coordinates or the difference between the coordinates of yours and the satellite, and that cannot be 0. So this part is 0, and if this part is 0, you get ATA inverse AT. So you get the estimate of x. So this is your GPS coordinate. So I know the maths is a bit involved here. The maths is a bit involved here, but yeah, this is worth doing because you get an idea that how things are working. There are satellites, there are triangulation method. You have many times may have heard the word triangulation of method, but I thought that you should know about this triangulation method, and it's not only, it just doesn't triangulate, you have to have a lot of approximations to actually do the triangulation. Okay, so this is in short what we do in GPS. Okay, once we are done with GPS, basically yeah, I have this thank you slide, but I will just tell you. So anybody wants to, so I don't see anybody pinging me on chat. So if anybody of you wants to ping me on chat, just ping me. Okay. So beyond GPS, there is another interesting technique which is called differential GPS. Okay, there is another important technique which is called differential. Okay, so in differential GPS, so what is happening is, so there are, so let me show you this picture. So there are GPS reference stations. there are GPS reference stations who collects data from GPS. There are GPS reference stations who collect data from GPS, and their exact location is known. Their exact location is known, so they can more accurately, since my location is known, they can more accurately calculate where the GPS is. And since if you are very close to those stations, you can also collect that information from those stations and do the GPS calculation. So what is happening here? You have some sort of assistance where you actually take it from another station. Okay, so that is differential GPS. We need not worry about too much. So I will now sum up the entire class, and I will come to this slide. Let me come to this slide. So what have we done? So we have done a very important thing of understanding how location can be tracked. And how do we get this location tracking system? We can get this location tracking system by using the satellites which have been made available for public use. So satellite for public use, and now we can get it continuous. So which of these things we have now covered? We have covered the outdoor continuous. So in this lecture we have actually covered the outdoor continuous. Now the next question would be that if we cannot use, but in indoor we cannot use, indoor no satellite, the satellite signal will not come. Okay, in indoor the satellite signal will not be available. So all these funky calculations which we did cannot be done by indoor. So what are the hopes in indoor? What are the hopes in indoor? So in indoor, one big hope is, what are the other signals you are getting? You are getting basically maybe Wi-Fi signals. Okay, you are getting basically Wi-Fi signals and cell tower signals. So you may get two types of signals. One is Wi-Fi signal, another is cell tower signal. Okay, so now if I take this help of these signals, and what would happen if I am near a Wi-Fi? My signal would be strong. Near Wi-Fi, signal would be strong. Okay, signal is strong. And far away, then it will be weak. So can I use this simple information and build up something which can be obvious? So we will do this next class. We will start radar in the next class and check with it. Okay, I will conclude now.